Hello, everyone, and welcome to the Hyperthesis. My name is Patrick,
I'm Liam.
My name is Feely.
and welcome everyone to episode number 4. Thanks for sticking it out through our introductions and talking about our research in the first 3 episodes. We hope you enjoyed them. If you have any other ideas, you'll figure out how to contact us a bit later in the episode. But first off, we're just going to start with some quick discussion about interesting topics that we found from the past week. They can be new or new to us, just something interesting that we can mention and encourage you to research after listening to this.
I guess I can start again with something. I came across a paper, and I forget all the details about it, but it talked about these things called Planck stars. And I really like them. So it turns out that quantum mechanics predicts this thing called the Planck scale, which is basically this minimal length scale. So if you think of everything as being continuous, right? You look at water and you think it's continuous, but it's actually made up of atoms, and you can zoom in closer and closer and closer, and eventually you reach this very, very tiny size that space-time can exist at. It exists discretely, called the Planck scale. And I explained it very badly, but that's kind of the gist of it.
So I actually was asked that kind of question today because we are trying to figure out units basically, because like what I do, kind of units kind of sketchy. You have to define your own stuff. And I was asked, okay, what in the physical system, what makes units have units? We have meters, centimeters, and whatnot. Where does that come from? And it sounds just arbitrary, like 1 centimeter. What is fundamental unit of energy? What is the fundamental unit of temperature? Like, where does that come from?
Mm-hmm.
I think my answer to that, I think today was, we set up like we set up those units for measurement. We know where absolute zero is, so that's at least we have a reference point. We know the speed of light. A lot of quantities of things we do can be written in c, speed of light. Anything even like a position can be written in c, right? And a lot of quantum stuff can be written in terms of h bar, or Planck constant divided by 2 pi. So I feel like, related to Liam, what Liam said a bit, people come up with Planck's length, Planck's time, and all this stuff to help quantify or define what is a fundamental unit in reality is.
Yeah, so that's exactly it, actually, is that it's the minimal length that you can have. I mean, predicted by quantum mechanics. Like, again, quantum mechanics and general relativity currently do not agree with one another, and that's kind of our big problem in physics, is what is this unifying theory of quantum gravity. But quantum mechanics predicts that you have this minimal length scale, which if you zoom in on space-time, the fabric of space-time, like to the point where it's so small, you have this minimal length scale, and it's really tiny. It's like 10 to the negative 35 meters or something like that. It's very, very small. But this constant, when you predict it's in terms of these fundamental things. It's the square root of h bar times it's h bar times the gravitational constant divided by the speed of light cubed, all square rooted. So I guess that comes back to what you were saying, is that you have these fundamental things like the speed of light, Planck's constant, the gravitational constant. They kind of give you these scales.
I feel like I've seen that constant before. Maybe was it in like a Einstein equation or something? Or it sounds so familiar, like a 8 pi g h bar. It sounds familiar.
I don't think there's any pi's in this, but I mean, at least that's what Wiki says. But yeah, so anyway, you see a lot of these things sometimes together. I think Hawking radiation, when he predicted that, he derived the Hawking temperature, which we talked about in our first episode, and that involves the gravitational constant, Planck's constant, and the speed of light. So you're combining like quantum mechanics, gravity, and relativity, or special relativity, I guess, all in like one single theory. So that was kind of like why Hawking was very, very proud of his derivation of the Hawking temperature.
So that's a Planck length, but these Planck stars, what are they?
So the big problem with black holes is that, well, there's many problems with them, but one of them is that you always hear these popular scientists describing them as a singularity, whereas, your star goes supernova, it runs out of fuel, the force of gravity is so intense that it pulls all this matter into this very condensed region, and it creates a black hole, where at the middle of the black hole, general relativity predicts that you have a singularity. You have a point of infinite density. You have some finite amount of mass compressed into an infinitely small point. And you always hear these, popular scientists saying that because it makes people be like, wow, that's fun. But anytime you have a singularity in physics, it means that your theory sucks usually. Or maybe it doesn't suck, but at some level it fails. So this idea of a Planck star is that basically that at the center of the black hole you have the singularity. It kind of exists because you can get infinitely close to this point. But if space-time is quantized, so if space-time are these little discrete chunks of stuff separated by this Planck length, then you can only get so close to the singularity. And I think the idea is that somehow that kind of regularizes the singularity and gets rid of it. And it's more in-depth than that. So all this matter that falls into the black hole, it doesn't get sucked into this single point. It actually kind of creates a star inside of the black hole. And it isn't exactly... all this matter isn't separated by Planck lengths. It's further apart than that, but it's because of the Planck length that it can do this. So it gets rid of the singularity inside of the black hole by having this kind of very, very compact star inside of the black hole. I haven't read this paper too much, but I really like that idea because it relates to my work, where you have this, again, in the first episode I talked about how you get this phase singularity at the event horizon. And by taking into account some minimal length scale, you kind of regularize it. So I like this idea of a Planck star because it sounds very much like what I'm doing. Whether it's right or not, I don't know. But I think it's pretty neat.
Very interesting. That almost sounds like at the center of the star, there's this just massive nucleus.
Yeah.
All the stuff that's fallen into the black hole. And some sort of super, super massive atom, or, well, I guess just a nucleus just sitting there in the center. That's fascinating.
Yeah, I think if you Google it, you get kind of a description of it. It's probably better than mine.
There's so many models that people come up with to try to describe these things. Planck star, maybe there's a white hole somewhere. There's so many, and most of them, actually all of them, are probably wrong, right? We don't know. It's like almost fiction at this point. It's just metaphysics. They just hallucinate. It's come up with new model that describe how black hole works, and sometimes it's very interesting. But I think even in the next probably 50 to 100 years, or even more, we probably have no idea. You can't get that close. It's really far away, the closest black hole even.
Yeah, so that's the other thing, is that's why I also like studying analog black holes, because we'll never be able to, well, I say never, I shouldn't say that, but very unlikely we're ever going to be able to throw stones at a black hole and see what happens. We have math that predicts things. We can see things indirectly happening from black holes, like these big orange blobs that were first published recently. So these first ever images of black holes, or the existence of black holes, and these analog systems I study.
Yeah, the the other issue is the gravitational field, right? If you happen to send a good telescope or detector there, and you get too close, the time dilates too much. And it's like, oh, that spacecraft stayed there for 10 seconds, 1,000 years pass on Earth, so we never get that signal back. So like, well, how do you solve that problem?
Yeah. Yeah, they're interesting. It's a lot of interesting stuff, but it's definitely requires a lot of work. I just like the idea of Planck stars. I'm biased, so I'll say that up front. I like it because I understand it a bit.
I guess we'll have to leave that up to future experimental physicists. Now that you theory guys have figured something out, it will be up to us to actually see if it's true.
Yeah, exactly.
So as a different topic, apart from Planck stars, which again sound just super fascinating, and I'm going to go read up more about them now. This was mentioned in passing by a geophysics friend, but they said that there exists a certain wavelength of radar waves that are produced by lightning in the atmosphere. And what happens with these radar waves that are called extremely low frequency waves, or ELF waves, that are very, very low frequency, so on the order of hertz, which for waves, light waves, is just super, super long wavelengths, very, very slow waves. When lightning strikes in the atmosphere, the ionosphere and the surface of the Earth act like boundaries for this wave, and they actually create a resonant cavity around the Earth where these waves internally reflect within that cavity. And so there's a whole section of physics called geomagnetism where they actually study the effects of these waves and how it interacts with the Earth, and they're able to discover different information about this. So it's just a really cool concept.
It kind of sounds like those whispering gallery modes, or galley, I can't remember which word, gallery I think, that our friend studies, where basically you have like these waves, or were they waves? I can't remember. I think so. You have waves traveling in like a circle, forced in there by some boundary, and they kind of amplify or create like a standing wave or constructively interfere. I'm not sure which, maybe all of them. And you get some cool things from that, and there's a really popular YouTube video about how you can create plasma in a microwave with grapes. It sounds like that.
Yeah, so I think the whispering gallery was like the relic of the past too. I think when people were making churches or like secret rooms, so they would have like a small space in the walls, or like some circular space when you can whisper and the other side can hear it quite loud. So I think it's some kind of constructive interference.
Yes, exactly. I believe the main concept, or the main place that you can actually see this, are in circular rooms, but St. Paul's Cathedral in London, you can go stand at one end, have someone else stand at the other end, whisper something, and they can hear it perfectly. So it's the exact same concept. And just like what Liam said, we know someone that has worked on these in the past, where you have light just, or some sort of wave just creating this nice standing wave within a sphere or a circular object. And that causes resonance, where it's able to just maintain its intensity and amplitude as it resonates throughout this sphere, whether it's a cathedral in London or the whole atmosphere of the Earth.
People use that a lot too, I think, historically, to design especially like acoustically sound buildings like Colosseum and stuff. Like they don't have amplification back then, like, but a person would stand in the middle of Colosseum and just speak and people would hear it, right? I think and they didn't do the really like rigorous mathematical construction of the theory or anything. They just, by the ingenuity, they just figured this out.
Yeah, so that's some interesting stuff to think about. Maybe we'll have to come back to some of those topics at some point. I always really like hearing about these whispering gallery modes. Maybe we should talk about the plasma grapes, because that guy came to our old university and talked to us about it. But yeah, we should move on we should move on to our primary topic today, which is going to be on computers.
So yeah, today we'll be discussing something that I don't think the three of us have ever really studied in depth, but we'll be looking at cryptography and computing. And with that, we'll also be exploring quantum information and computing, because quantum computers are really becoming the big thing in physics. I know at least at my university, there are several labs working with $1 million machines trying to produce quantum computer-like systems where we're able to store information, but it's quantum information. And I'm sure we'll get to disentangling what all that means, but I think first of all we should start discussing the basics.
Yeah, so if you want to understand quantum computing, you should probably understand what we call classical computing. So, my laptop in front of me works. It's a classical computer. So again, we're not experts in this, but this is our hand-waving description. So what is a computer, right? So computer is kind of this collection of many electronic circuit components, essentially. And what does it do? Well, it kind of you take some kind of input and gives you some kind of output. I don't know if any of you guys want to elaborate on that, because I don't know exactly how they work.
Yeah, so I have looked into this a bit, and classical computers are exactly what you said. You put in some sort of information or something, and you get something out of it. And to undergo some sort of transformation between the input and the output, you have what are known as logic gates. Now, logic gates in modern computers are set in such a way that they use transistors, these newfangled things that we've actually had for, I think 60, 70 years at this point, maybe. So these logic gates consists of different arrangements of transistors so that they're able to apply logic to the input. So for example, if you had, as an example of a very simple logic gate, which is an AND gate, if you had just, say, input 1 into a computer, and then you also input another 1 into a computer. If you have an AND gate, it will say, okay, so if they are both 1, then it will output just one number, which is a 1. So it's able to take in two inputs, in this case, two things that say, okay, this is number 1. It compares them, again, using a complex arrangement of transistors, and then it spits out, okay, it's a 1. Whereas if you were to put in a 1 and a 0, it would output a 0, because those are not the same. And so it's saying that if it's a 1 and it's not a 1, then they don't compute with the logic, and so it outputs a 0. It's a very brief overview.
Yeah, so there are these kind of like basic requirements a computer has. So one of them is it needs memory, and the second one is that it requires initialization. So if you put in these kind of 0, 1, 0, 0, 1s, so on, it'll apply some kind of logical operation to it, like these AND or gates, like you've described. And then one other requirement, which is a very important one, is that it needs to give you this final result with a very small rate of error. So if you tell your computer to print hello world, or you say, give me 1 + 1, you want it to work every single time. You don't want it to work 80% of the time, right? Because that wouldn't be very useful. If you send an email to your coworker and you say, like, how are you doing? And it comes out just muffled garbage or whatever, like, you don't want that. And classical computers are very good at having very low error rates. So when I think of computers, I always got very confused at, like, what are these 0s and 1s, essentially, right? I was like, well, I know that 0 and 1 represent states. So if you send a signal, it could be 0, it could be 1, or it could be a whole bunch of them. But like the simplest case is it's either a 0 or a 1, right? So I always wondered, what does that mean? And I don't really know how it works with the transistors and all the circuit components, but one really simple way to think of it is that this information is kind of described within the computer by voltages. So all these circuit components kind of tell you a 0 might be one component is at 0 volts of potential, and a 1 might be it's at 5 volts. And these are just dummy numbers. I don't actually know what they are, but they're nice numbers for us to think about, 0 and 5. So if you send a signal, a 0, the circuit component has 0 volts, and if it's a 1, it has 5 volts. And the reason why they have such low kind of error rates is because your computer interacts with this environment, right? Like one simple interaction is you give it a command, that's one, but if your computer exists in any environment, like if it's in the room with you, there's light shining on it, there's air in the room, there's thermal effects happening. You don't want that to affect these voltages and mess up your signal. So by using 0 volts and 5 volts or whatever they use in real computers, again, these are just dummy numbers, but the fluctuations that the environment has on these are very small. So it might be like 4.95 volts. It might, like if you send in a signal as a 1, some error might change your 5 volt signal to 4.95, but that's basically 5. So it works very well with all, and that's what's really nice about classical computers is that this error rate's very low. And there's also methods to correct the error, because there's always going to be error or fluctuations or interference with the environment.
It's also important to emphasize just exactly what a transistor is, because you said it could be variable, so it's 0 but not quite 0, or 4.95 volts instead of 5 volts. And that a lot of that error is corrected because we're using transistors. So transistors are made out of semiconducting material. So semiconducting is not quite like copper wire, where if you always apply a voltage to it, it will always conduct. And it's not quite like an insulator, where if you apply voltage to it, nothing happens or it lights on fire, because it's a piece of wood that you've stuck in between two electrodes. Instead, a semiconductor, it depends on what kind of voltage is applied. And its atoms are arranged in such a way, and extra atoms are added to a semiconductor to allow it to have a voltage applied to it, and depending on the voltage applied to it, can let across an even larger voltage. So it's kind of like a light switch, where if you were to go up to a light switch right now, hold it very steady, and then just move it up and up until the light turns on. That's essentially what a transistor does, but on a very smaller scale. Instead of having that mechanical motion of, okay, you push it up and up until the light goes on, it's you apply a bit more voltage to a part of it, and a bit more, and then suddenly the switch is flicked and a whole bunch of current is running through it, and the light turns on.
Yeah, this discussion reminds me of this mechanical machine where, if you go to like a fair or something, they have these pins on the wall and you drop balls from the top. And, you try to get into certain holes, but what you can do with those, if you don't play the game, you can put doors, like gates on them. So those can also act like logic gates. If you have two balls and you want to add them, you just put two gates that blocks from going other ways, and those balls would add them to go to one hole. So in transistor, you can also make kind of equivalent mechanical circuit there, where you're like, if there's enough balls there, if they add more balls to it, because the gate would open. I think that transistor is such a fundamental to computer that it's like, if you see any computer manufacturer to be like, oh, this CPU has 1 billion transistors, 2 billion transistors, it just get insane.
Yeah, transistors are very important. I think the guy who came up, well, maybe it wasn't one guy, but the group or whoever came up with them, I think that was a Nobel Prize. He might have won 2 of them, actually. I forget what the second was for. Maybe I'm wrong, but I know transistors, they were like the big kind of turning point in computing. And, Patrick will tell a story later that involves computing and some other things. But, right, yeah, it's really interesting how computers kind of run through these logic gates, and it's really cool because, I mean, if you've ever played Minecraft, right? Redstone is just logic gates. People in Minecraft have created working computers within the game using these logic gates. It's really cool. Yeah, no, it's really neat how you can do that with Redstone in Minecraft. But anyway, back to quantum computing. How does that have to do with classical computing? So this key point of classical computing, like I said, is that it's kind of robust against this error or these environmental effects. You can always distinguish if it's in a 0 or a 1 state. There's very little room for error there, and that's why computers on your desk work.
Right, and so just to preface the discussion about quantum computers, I think it might be important to mention Moore's law and just where the transistor is going, because it is so reliable. So why do we need something better than the transistor if it has such a small error rate? So the transistor was invented in 1947, and you're right, it was by a group of 3 people, John Bardeen, Walton Brayton, and William Shockley, and that was all the way back in 1947. And since then, it's been getting smaller and smaller and smaller, to the point where Moore predicted, I believe it was in the 60s, that every 18 months, the size of the number of transistors that will fit in the same area will double. And so generally for the past 50, 60 years since Moore suggested that was true. But we're getting to the point where if we go too small with a transistor, the error rate will increase. And that increase in error rate is caused because of quantum effects that are happening at the level of the size of the transistor. So this is a very important issue because we're trying to get better computers over time, and that's starting to fall off now. So Moore's law is kind of broken at this point.
Yes, to add on to that, like I think these days they're around they like a 1 digit of nanometer scale. So like to even make that, like how do you even put there, right? I think the technique they use is photolithography. So I think lithography is like, you scrape or like put really thin stuff on a surface. Or I think they just shine a light to basically create these shallow cuts on the silicon surface. That's why silicon is so important to making all this CPU. By this, having silicon shortage really affects the CPU market and stuff. Like the photolithography actually like shine, I think, either laser or light to actually create this pattern that turn out to be transistors.
It's really interesting that you mentioned the lithography, because that's the traditional way of making transistors. But because that they're getting smaller and smaller and almost too small, they actually have to look into 3D production of transistors. So they have been able to come up with a way where they produce essentially 2 transistors stacked on top of each other from the same piece of silicon. So instead of doing the traditional lithography where you apply a protective layer and then essentially erode away with chemicals the exposed pieces to get your transistor working properly, they have a different technique where they're able to essentially create stacks of transistors on top of each other with the same piece of silicon. It's just a fascinating side note.
Yes, I remember the 3D printing that the 3D that's just like you're in a liquid that just shine just light into the solidify certain part that is basically the shape just comes out of almost nowhere, right? I feel like if you can do that in a smaller scale, you can create a transistor by even not having to put a probe in or a head to actually physically create something.
Yeah, it's really cool how much you can do with lasers. They're a really powerful tool that was discovered a while ago. And it's a whole area of research now where, I mean, I don't know the technical terms, but they're basically like these quantum transistors or quantum batteries, or they're like the classical equivalent, but very, very tiny on the scale of the size of multiple atoms kind of in one little grouping and stuff like that. So it's really cool.
Yeah, the field of photonics, I think, is huge, right? Like photo, light, and tronics, just electricity and stuff. So I think like all these technology depends on the field of photonics. So I think a lot of people who do like higher education in physics, in photonics, end up working for companies that make hardwares that to actually like advance tech, try to advance technology of mankind, like on the cutting edge, basically. So I think we should get back a bit on quantum computing. We talked a little bit about classical computing. Quantum computing, like Patrick said, is kind of thought to be the solution to this limit of speed. And by exploiting basically or taking advantage of the nature of quantum systems.
Yeah, that's exactly it. So classical computers are great. They can be pretty fast. You get these big supercomputers that can do these beasts of calculations much faster than my phone can, but we can do better. We have quantum mechanics in our tool belt. So classical computers, you have these two states, these 0 and 1 states, these bits as they're called. But quantum mechanics can generalize this. So you've probably heard of Schrodinger's cat. It's the idea this cat's both dead and alive until you observe it. So the idea of you interacting, taking a measurement on this cat, and this interaction can be, it's not you looking at the cat, but it's the idea that like you shoot a photon, it hits the cat, it bounces off the cat, and then it goes into your eye. That's an interaction, or it could be any other form of interaction. But you actually observing this kind of collapses the cat's wave function, as it's called. So it forces the cat to be either dead or alive. That's kind of the analogy. It's kind of silly, but Schrodinger himself actually really hated that analogy, it turns out, because we don't see superpositions of macroscopic objects, and that's because of things interacting with them. But I'll get back to that. So quantum mechanics, you can exploit this. You can have actually a superposition of bits. You can have some amount of the 0 bit plus some amount of the 1 bit representing the same state. And that's it turns out that you can, just from that simple fact, like mathematically it's a simple idea, but you can just skyrocket the speed at which you do calculations. And it's called quantum supremacy, is the idea that a quantum computer can do a classical computation faster. And it was actually first achieved, I think, in 2019. Or it might not have been the first time, but it was the first significant demonstration of quantum supremacy. So in 2019, this group, and again, I always forget the names and where they're located. I apologize to them. But in 2019, there was a calculation that would have taken like state-of-the-art classical supercomputer 10,000 years, and a group did it in 200 seconds. So that's pretty impressive. Something that would take 10,000 years, we will certainly never see that calculation complete. It took a quantum computer 200 seconds. You go microwave your coffee or something, and by the time it's like microwave your coffee, make a sandwich, and by the time you're done, this calculation is complete. That would have taken 10,000 years. So you can kind of see why it would be useful to have quantum computers.
I must say, if you were to have a microwave close enough to a quantum computer, that might not end well. And that's because quantum computers are great. They have many advantages, but not in every application. So you probably wouldn't be seeing a quantum computer replace the chip in your laptop. And that's because they have some disadvantages.
And that's exactly it. This is the reason why we don't have quantum computers on why our phones aren't quantum computing, why my laptop isn't a quantum computer. Is because it turns out quantum mechanical things are very, very, very sensitive to something called decoherence, which basically means that they interact with things in their environment. And that's the huge downside of quantum computing. And that's why conceptually, it's very easy to say we're just taking superpositions of a 0 bit and a 1 bit. But the big problem is that if this system interacts with anything, so the environment, or even if you input something into a quantum computer, that's an interaction. You've now collapsed the superposition of states to a single choice, and your computers now become classical. So it's very hard to create these systems, it turns out, because of decoherence. That is the big problem. You need to isolate them very well, and it's very hard to do.
Well, if you look at what we study in physics, right, to obtain the quantum limit or to observe quantum effects, we have to go to like ultra cold atoms, like nanokelvins. That's like really close to absolute zero, just to see some of the quantum effects. And we try to do that in macroscopic scale-ish to create a computer. Like, they have to be super cold to do this? Like, it's crazy.
Yeah. Obviously, it's not ideal if you're trying to type on your computer and it's freezing your fingers off. But these ultra cold systems are really, really nice because, again, this is kind of the stuff I study, so I know a little bit. But they're so nice because you can really fine tune them, and you can test all of these kind of ideas that come up in quantum information and quantum computing. But the end goal is that you want something that works, in 20-degree weather or 30-degree or, whatever, something that's not 10 Kelvin or less. So it's very hard to do, it turns out. And that's a huge area of research, because if you make a quantum computer, well, you're a billionaire right away, I'd say.
Just to take this from an experimentalist perspective, if you've ever seen these devices that are capable of producing quantum computers, or where quantum computers are made, they're just incredible things. We have a couple at the University of Alberta that I've had a privilege to see a few times. And just to describe them for you, these devices are the size of a small room. They are noise isolated, so no vibrations can get to them from the outside. I know the ones at the University of Alberta are constructed on their own concrete pillars in the basement, so separate from the building. Then you have, they tend to hang on these massive dampers that are tuned to remove any extra vibrations that come in. And then usually what you'll see, if you look up a picture of, say, a quantum computer, is this giant mass of wires hanging down from these dampers. And that's usually sealed in a cylinder that's kept in, it can go down to the microkelvin, the millikelvin, and I think some have even gone to the nanokelvin. And these are very, very intense refrigerators. So just if you're looking at a picture of a quantum computer ever, just know that most of the things that you see there are refrigeration systems. That's most of the mass, and then the physics is happening actually in like probably a really small box somewhere in that system.
Yeah, I just want to remind everyone that 30 years ago, computers are the size of a room. Now we're talking, quantum computers are the size of a room. Well, I mean, let's wait 30 years. And I want to also get on into the quantum information a little bit that Liam mentioned, because quantum computers are kind of have this, the prediction that they're gonna make all the encryption obsolete. They can solve any password. They can solve any type of encryption that you put on the system. So I think the idea, the field that's been investigating more now is the quantum encryption. How do you encrypt your data, encode your data such that quantum computers cannot break it easily? Yeah, anyone have any ideas on that stuff?
Well, I know traditional encryption tends to work based on prime numbers. So there could be an infinite number of prime numbers. We're not quite sure, but that's a whole other discussion. But essentially how encryption works is if you take two different prime numbers or a few different prime numbers and create a number as a multiple of them, then when you go ahead and decompose that number, you arrive back at prime numbers. And using this, I'm a bit fuzzy on the details, but essentially what you can do is use the existence of these prime numbers to make a cipher for how, let's say, an email that you write is converted into a different text. So it's essentially a key that you can use to convert the different bits, so the ones and zeros, in different orders, and then you send that key along as well, and using that same sequence of prime numbers, it can flip the information back into the email that you're reading. I'm assuming, I don't know, but that quantum computers are able to do something with prime number calculations. But Liam might have more to say on this.
Well, maybe not that last comment, but yeah, so you're 100% right. That's kind of how encryption works. That's why when I go in my bank and I do an e-transfer, it's why it's safe. It's encrypted. I mean, I hope it's safe, but allegedly it is. And it has to do with factoring prime numbers, because you think of prime numbers like, they're really easy to like multiply together. Multiplying things together is very easy, but it turns out factoring them is quite hard. So for example, like factoring 15, 5 times 3, that's an easy one. But for bigger prime numbers, it becomes quite difficult. And 15 is not a prime number, obviously, but you know what I mean. The higher you go, the harder they are. It involves factoring these numbers into prime numbers. My bad. So that's how classical cryptography works. But these quantum computers would be able to factor these numbers a lot better than classical computers. So I'm not quite sure exactly how they work.
My guess would be because quantum computer relied on finding probable ground states, right? If you can set up your system such that the ground state would be the 2 factors of that number, and you just do some magic to get into that ground state, and hopefully that magically appear. And also, I think to tackle with that is if you make your password or your encryption to change every time you observe it, unless you observe it right. I think that's also one way of doing quantum encryption.
Just from what I understand with quantum computers, and thinking about how they're able to compute these prime factors, to me it seems like you can't have a computer with just one quantum unit, qubit, or you have to have multiple ones, because to be able to calculate these numbers, the individual pieces of a quantum computer need to interact, and then that interaction will essentially, if you looked at mathematically, produce a wave function that has a peak somewhere, and that peak is your answer, kind of thing. And so I'm actually curious about this. Do you guys know if you can have a single unit quantum computer?
I do not know. Again, as a theorist, I tend to not think about these things, but maybe I should be.
Well, if it has one unit, well, it probably can have a state, but can it compute? That rely on, so you said rely on coherence. I mean, something cannot just cohere with itself, right? It has to cohere with something else. Like you have to entangle with something.
Right.
I think that the concept of entanglement is huge in quantum mechanics, right? And I think when it decoheres, it loses its entanglement state.
Yeah, I think that's all related to this thing called the Bell state. This thing called the EPR paradox. But anyway, I don't want to get into that, because every fact I say will be very wrong, because it's been a while since I've thought about that. But we definitely learned about that in our undergraduate Quantum 2 class. But yeah, so that's kind of a little, I don't know if you guys have anything more to say, but that's kind of a little overview of computing, quantum computing, cryptography, quantum cryptography. Patrick?
Yeah, it's a very fascinating topic, and there's always new research coming out. I'd be curious to see, if you've searched an archive, how many papers are relate to quantum cryptography and quantum computers, but will definitely be interesting to see where it goes in a couple of years.
Yeah, on my way to work, on the bus, I usually scroll through the archive. And for people who don't know, the archive is this kind of like open access preprint for journals. So if you want to publish in a journal, usually you put your publication in the archive first, and your peers can have access to it for free. So like you can go in the archive and read any of the physics papers there. And usually what you do is you send them kind of feedback and say, you'll see a paper in your area and you'll ask them questions and be like, what about this? What about that? I think this is right. I think this is wrong, and so on. But yeah, so scrolling through the archive on the bus in the mornings a lot of time, I think like every like 3 out of 5 or 4 out of 5 papers is on quantum information, quantum cryptography, quantum computing. It's kind of the big thing right now.
Yeah, so different on the fields though. Some journal don't like you putting stuff on the archive, so they actually require you to not put up anything up that is public. But also a lot in computer science and such, the publication is different than like in physics or hard science, where it's actually you have to do a lot more rigorous investigation in terms of mathematics. You have to make sure your data is ethical and all these rules you have to follow, where a lot of computer science research, the cutting edge stuff are not in the journals. They're actually on like conferences papers. So you go to a conference, you have a little paper you publish on, and people just go on that and reference that instead of a journal.
Just to note, I did search on archive just now. So for quantum computing, there's over 32,000 entries in archive. And just for reference, I searched dark matter, which has been around for, I'd say, a little bit longer, at least the idea, than quantum computing. And that only returned almost 40,000 results. So quite a bit on quantum computing.
So I think today, since we talk a lot about computers, so Patrick has a little story about almost like the history of the first computers and how it has come forward. Would you like to take it away?
Yes, and before I tell the story, I would just like to let you know how you can contact us if you have questions about the show. If you would like to suggest some topics, feel free. We can be reached at our Gmail at hyperthesispodcast@gmail.com, or you can find us on Instagram at the Hyperthesis. Feel free to reach out to us, send us a personal message, and is it like the page for Instagram? I ask our social media relations guy.
You wanna follow the Instagram page, but you do want to like all the posts, of course.
There you go. Perfect. And our podcast can also be found on Anchor FM. That is where we are based. So it's Anchor FM, anchor.fm/hyperthesis. We can also be found on most major podcast programs. So Google Podcast, Apple Podcast, Spotify. We can be found on all these different platforms. So feel free to find us and share us with your friends and family and strangers. So moving on to a story. Since we talked about cryptography and computers and encryption, I think it's important that we discuss a very important player with cryptography and encryption. So maybe not the founding person, but someone who has had a profound effect on the world of computing and of cryptography and all these different aspects of computer science. So today we're going to talk a little bit about Alan Turing. Before we begin with him, though, I'd like to take you back maybe a few centuries, to when computers actually first existed. So what we talked about today were classical computers and quantum computers, but these are both relatively new ideas. Quantum computers more so, but even these classical computers are fairly new ideas where we're using electricity to do the work for us. Now, before these electrical computers existed, there used to be a mesh of electromechanical computers. And before then, we had what are known as mechanical computers. These are complex, for the most part, instruments that are used to do computing, except instead of using electricity to do the work, they use different gears and drives and all of these things to do the work for us. So the first mechanical computer came about most likely around 1200 Common Era CE. And at this point, they were simple devices. They were used for timing. So I guess technically a pocket watch, if you have an old wind-up one, is technically a mechanical computer. That might be controversial to say, but if you'd like to refute that, let me know. But these mechanical computers have existed for quite a long time, and they've been used to decode mysteries of the tide, so how we can tell what the tide will be a month in advance. If you've ever wondered that, nowadays we figure that out based on classical computers, but this was actually a very big problem, and it took a mechanical computer to actually compute tide times around the world, and that was based on the sun and the moon and the motion of the earth and where you are on the earth, which is a lot of variables that's very hard to deal with analytically in math. But if you let a computer do the job, much like today, it tends to be a lot easier. So mechanical computers were very important for doing different functions throughout history. And if you'd like to learn more about them, there is actually a very good video on YouTube from Derek of Veritasium, where he goes over the history of mechanical computers.
Yeah, so kind of add on to that, there's this guy in like the late 1700s, early 1800s, who kind of the father of the first computer, and it was a very mechanical computer, but Charles Babbage, I believe. I don't know if you're going to mention him later or not, but him and his son created, I forget what it's called, a difference machine or analytical engine, and it had to do with kind of factoring polynomials or something like that. But it was kind of like it was this huge thing. It was 25,000 parts, 15 tons, like this massive machine. But it was kind of the first modern in quotation marks computer, I guess.
Well, in your standard, Patrick, would an abacus be a mechanical computer? I mean, it's thousands of years old.
I would argue that no, because it still requires the person to keep count in their mind. Yes, it does keep count, and it's able to do incredible maths. If you've ever seen someone doing math on paper versus an abacus, the abacus almost always wins. But I wouldn't necessarily consider that a mechanical computer. But I would classify what Liam's talking about, for example, a mechanical computer, because you're using these mechanics to do the math instead of having that human involvement as well to manipulate the computer itself. So I guess there's a level of manipulation that might be the defining line. Again, I'm not too sure. But these are mechanical computers. They are fascinating devices, and I would recommend looking into them. And they were still somewhat common around the time of 1912 when Alan Turing was born. He was born in London, so he's British, if you didn't know that. And he became a mathematician who studied both at Cambridge and Princeton, so very big schools. And during that time, he worked with the British government as a code breaker. He was someone who helped decipher encrypted messages and worked with decryption. So he was still working for the government by the time World War II broke out. Now, it broke out in 1939, and so he was still a fairly young guy, only 27 years old, working for the British government. So quite young, if you think about the person who finishes a PhD, for example, they're probably a bit older than that, depending on what field you're in. So a young guy, and he's working for the German government, trying to help with cryptography. And one of the big issues at the time was trying to intercept German communications. Now, the Germans had a very complex system of encryption, such that they could relay messages to each other without worry of it being captured by the wrong hands from their point of view and being used against them. And in particular, their U-boat missions were particularly devastating because they could know where to attack, and the British or any of the Allied forces had no idea what was coming. So this device that they used was known as the Enigma machine. Now, this Enigma machine was a mechanical computer. Again, they were still being used at this time. And this mechanical computer was able to be typed into, and based on tumblers within the computer that could be set and removed and replaced, so that way the encryption changes, you could type out a message. It would be encrypted by this mechanical computer, sent along with the details about what the encryptors were programmed to, again, all mechanically, and then it could be decoded by someone with a similar machine. Now, this was a very complex machine. Decrypting it was worked on first by many people involved with the Polish government, because Poland was right beside Germany. They had a lot going on for them, to put it mildly. And so they really were trying hard to break this encryption, to find the cipher for this Enigma machine. And meanwhile, the war was going on, so it was very desperate to try and get this Enigma machine broken and the code cracked. And to add to the complication, the cipher that was used with these Enigma devices was changed on the daily, so it made it even harder to break the code because there was no consistency. Now, with that being said, it would take a person many years, if at all, to crack these codes. And in wartime, years is too long. Kind of like how you talked about how it took 200 seconds for a quantum computer to crack something, when it would take a classical computer 10,000 years. This was very similar, where it would take a person far too long to decode it. So, what did they turn to? But computers. Now, these weren't quite computers that we know of today. Again, the transistor hadn't been invented and wouldn't be invented for another about 12 to 15 years, depending on where you were in the war. So, instead of using a computer with transistors, they used electromechanical computers. And so the work of both Alan Turing and Gordon Welchman, they combined to create what's known as the bomb, or this decrypting computer. So this electromechanical computer could attempt to decrypt these codes by testing many different iterations of decryption ciphers at the same time. So instead of doing the work of one person or many people trying to decrypt it, it could work methodically through, say, a message that they got and any additional information to try and break this code. And so the machine itself was built by Harold Keen, and it was designed again off Polish cryptologist Marian Rejewski, if I pronounce that right. And so it worked through a process of deduction and having these rotating cylinders that had electrical contacts. And as it worked through different possibilities of ciphers, it would either fail or succeed. And eventually they did succeed. So in 1941, Alan Turing and the rest of the team were able to crack the Enigma code and intercept messages and understand messages sent to the German Navy. So now they could know the whereabouts of U-boats, and this really was an important effort in both the war and defeating the Germans, as well as helping with a small battle, such as the Battle of the Atlantic. So because of the work of Turing and of Welchman and all these other people, the war is said to have been shortened by quite a bit and maybe was less severe. It's hard to tell if we ask what if, but these are very important things. Before the war and during the war and after the war, Turing still kept on with computer sciences. He proposed different things like the Turing test, which is a method to detect if an AI is actually intelligent. It's not like Siri nowadays where it's an AI, air quotes. Instead, it's an actual intelligence that's able to communicate and is no different than talking to a human with some sort of interface. He also came up with the Turing machine, which is a mathematical concept involving an abstract machine that is able to prove the fundamental limitations of mechanical computers. Now, modern computers work off of different concepts than what Turing had around him at the time, so it's not quite the best thought experiment nowadays, but still incredible to think what he came up with back then. Now, unfortunately, he was arrested in 1952 for homosexuality. He was chemically castrated and committed suicide in 1954. And his work wasn't actually released until the 70s, when the information about the war became declassified by the British government. But because of his work, we have modern computers. That might be a stretch to say, but it's because of him that we were able to figure things out with computers. And there's a lot of great honors now that are named after Turing, including the highest computer science honors. And really an incredible person faced with a lot of challenges, and we have computers as we know them because of it. And if you'd like to hear a better told story, I would encourage you to check out The Imitation Game, which is about Alan Turing, for, I guess, a more dramatic take on events. But even so, his life did seem pretty dramatic and came to a very sad end, unfortunately.
Yeah, it was very unfortunate. A man who did so much for his country in the war was then arrested for it, and drove him to do that to himself. It was very one of the great shames of the British government. But yeah, very, very interesting stuff.
Yes, so thank you everyone for joining us for this episode number 4 of the Hyperthesis. We will be back again with episode 5, and we hope you enjoy.
Bye.
Bye, everyone.